we left off. Switching gears. So, of course, you knew we got to get to this with climate change, right? So how do humans in modern times, how have we affected the climate? And of course, we all think about fossil fuels, but the other thing that we've been doing with regard to climate, even before we were burning fossil fuels, was clearing forests, doing things that Mother Nature randomly would not do, probably agriculture related. And for instance, we've talked about albedo, as you clear a forest, you change the reflectivity of the land, and also as you clear a forest, those trees were great at using photosynthesis to convert carbon dioxide to oxygen. So that's the other kind of problem. This over here on the right is something actually from chapter 13. It talks about how much we rely on burning fossil fuels. So fossil fuels are coal, natural gas, and oil, or petroleum products. Okay, so remember the way this works is, those are all fossil fuels, and you can kind of see what sectors they go to: transportation, industry, residential, commercial, electrical power. So with burning fossil fuels, of course, one of the primary products of burning a fossil fuel is carbon dioxide and water. Okay. All right. Oh, yeah, here's the other thing. If you ever get a glass of water from the sink, your cold tap water, it's nice and cold, you enjoy it, then you set it down, and then you come back after a while, and your cold tap water is warmed up, and have you ever seen like bubbles kind of on the edges? Okay. What happens is when you got that cold tap water, there was just like regular air that was dissolved in your water. And as water warms, gases are less soluble. So basically that is basically degassing. Okay, so when we talk about the oceans warming, actually then the carbon dioxide is less soluble in the oceans. Okay, so increasing carbon dioxide levels. All right, so prehistoric, I just meant to say like way back levels. So for instance, down here, the way you read this is today. And then over here, this was 400,000 years ago. Okay, so this is going back in time. So actually, we've had a few, if you count the peaks, this is a peak, this is a peak, 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 okay? Then of course here we are in the present, and kind of that upswing, sometimes they call that the hockey stick, so where it kind of goes, the carbon dioxide spikes up. That is actually mostly due to the Industrial Revolution, or about the time the Industrial Revolution was really kicked in, burning fossil fuels. So my point is that these peaks back here occurred without human influence, okay? But I would say, or your textbook would say, that right now we're up here, okay, and we are 30% higher than the highest carbon dioxide content in the atmosphere, going back not 400,000 but 600,000 years. Okay, so definitely have something going on with regard to carbon dioxide in the atmosphere. So I was thinking, now why do we have these natural fluctuations kind of going back before humans were here? And you figure there's volcanic activity, and then there's kind of this cycle with temperatures might bring different plants and animals, so that changes your carbon dioxide in your atmosphere too. Oh yeah, and so these back here, this was all obtained by ice cores, like the cute little carbon dioxide molecules that were stuck in ice cores. And this right here though, and actually in 1958, this was taken from that place in Hawaii we kind of looked at before. Okay, so carbon dioxide. Well, what's up with carbon dioxide? Well, we talked about it before. Actually brought in this this figure down here from chapter 2, and it kind of talks you through 1, 2, 3. It kind of talks you through the stages of what carbon dioxide does in our atmosphere. So, of course, we talked about solar radiation coming in, hitting the Earth, and as it hits the Earth gets warm. And so the Earth, once it's warm, it wants to ooze off its radiation. And actually, that's what's happening here in the middle one. So where carbon dioxide comes in to play is right here in the third box. So I don't know if you can tell, but basically those little bug-looking things are carbon dioxide and water vapor. And so they are actually driving that thermal energy back into the Earth. So that's kind of the greenhouse effect. So how do we know that Earth is getting warmer? Well, we can take a look at both the surface temperatures and the sea surface temperatures. We can see the the melting of the cryosphere, okay? And we can see sea levels rising. Now, did you guys see that Gilligan's Island episode where Gilligan was upset because the island he thought the sea levels were rising? And it was like the stick was changing on him, and he was like measuring it the wrong way. It was so funny. They all had to evacuate, and they didn't know what to go to. Okay, so let's see how this strikes you. So just surface temperatures, we're looking at the last 100 years, the temperatures have gone up 1.6 degrees Fahrenheit, which doesn't seem like much, but it is. And stuff has to melt when temperatures rise. So since, let's see, about 45 years, yeah. In about 45 years, though, of that 1.6 degrees, one of those degrees has been in the last 45 years. So basically you get, 0.6 for 55 years, and then 45 years you get 1. Does that make sense? Okay, and so, like the slide says, the warming process is escalating. Okay, so where is the carbon dioxide? Well, let's see, is this right? Yeah, no, this is about global temperatures. So there's this organization, and I kind of remember a few years ago when their document came out, okay? Trying to stay apolitical about this, but the governments of the world, scientists got together, and they are part of the Intergovernment Panel on Climate Change, okay, or the IPCC. And they looked at warming, okay, and so kind of the warming is kind of summarized down here by decade, okay. Along the x-axis is, what we talked about, kind of I don't see 1.6 there, but, oh yeah, because it doesn't go back to 100 years ago. But that's kind of the 1.6 and 1 degree we're talking about by decade. But not only did they look at warming, but they looked at what is the source of the warming. Now, this is where, I don't know, it seems like logic says that temperatures are warming, but then what's causing the warming? And this is where they said it's you can look at the natural causes, like we looked at natural causes for climate change, but it's 95 to 100% likely that the biggest impact is human impact that's making our temperatures rise. So over here, and I think this is still part of maybe the same study, this is where I said, we use numerical weather forecasting to come up with what tomorrow's forecast is going to be. So this is where they use computers and models, and they try to anticipate. This is using 3 different models to anticipate how our temperatures are going to go up. And I can apologize, I kind of lost the y-axis, kind of hiding behind that slide. Maybe it is 4 different models, 4 or 5 different models. So, anyway. So, carbon dioxide, CO2, just a natural outcome of burning fossil fuels, but CO2 is not the only greenhouse gas. We said water vapor is a greenhouse gas, and other greenhouse gases are methane, and this is where I giggle, because methane, of course, is put out by livestock, and there was, they didn't do it, but Congress was saying we should have tax on cows, because they're an emission source for methane that can be a greenhouse gas just like carbon dioxide. So a couple of different things in the farming industry, nitrous oxides are also associated with fertilizers. So with regard to those emissions, I mean, that does not look very, I thought this is weird. So this is the year 2016-ish, okay? So is this like the year, I just think that's weird. Bless you. Anyway, so there we kind of see an uptake in both methane and nitrous oxide as our farming has improved. This actually right here is kind of a blow up of this right here. So your book says that individually they're not a problem, but collectively they are a player. So another human impact on climate potentially is this idea, an aerosol. So you can kind of see, there's a figure from your textbook, this sort of haze looking thing right here, that's the corridor of haze coming from China. And I'd have to look at a map, but doesn't that look kind of like, this is north, south, is that your easterly trades? Taiwan. Wish I was better at geography. China, nope, I got that wrong. Japan. Anyway. Okay. So anyway, with that haze, actually, it can block incoming solar radiation. So like this slide says, wow, it can have a cooling effect. But like your textbook says, that cooling effect does not counter the warming effect of greenhouse gases. So nice try. Okay. So there is this concept, and it doesn't just happen in climate change. It also happens in other things. And it kind of reminds me of like Pavlov's dog study, where basically kind of conditioned a dog to salivate at ringing of the bell. Do you remember that? Okay. So a positive feedback, like if somebody gives you positive feedback, that means you want to keep doing what you did. And so a positive feedback mechanism actually enhances the original thing. So I kind of talk about this change A results in change B, which reinforces the first thing that you did. That's a positive feedback mechanism. Now, it doesn't mean in the case, like in the case of doing something good, it doesn't mean that something good is going to come from a positive feedback mechanism. It just means that it's going to be reinforced. So a negative feedback mechanism is kind of like the cycle is broken. Negative feedback mechanism, the cycle is broken. So basically, something happens A, and that something A promotes B to happen, and B actually dampens A, so it makes A less likely to happen. So it's breaking the cycle. So that's a negative feedback mechanism. So examples of a positive feedback mechanism look like this. So again, it doesn't mean that it's a good thing, it just means that it reinforces the first thing that happened. So let's start with, let's see, I'm going to start with warmer oceans. So I'll put a 1 next to warmer oceans. Okay, with warmer oceans, we have more melting. With more melting, we have less ice. With less ice, we have, the ice is good at reflecting solar radiation. So your albedo changes. So basically, with less reflectivity, it actually goes ahead and absorbs more. Okay, and if it absorbs more, then your oceans get warmer. So basically, you know, this was A and all these were B, and it reinforces what you started with. Okay, so that's a positive feedback mechanism. Doesn't mean it was good, it just means it reinforces it. But now here's one actually starting with the same initial event, warming, and it actually, in this case, it's a negative feedback loop, negative feedback mechanism. So here we go. It goes something like this. So we start with global warming, and of course, as this temperature of the Earth increases, you're going to have more evaporation. If you have more evaporation, you're going to reach 100% relative humidity faster. So you're going to get more cloud cover. And as you have more cloud cover, it's kind of like your aerosols. More cloud cover will block incoming radiation. And as it blocks incoming radiation, of course, like I said with the aerosols a minute ago, you're going to have a cooling effect. So there's where, in this path, global warming actually ultimately the cycle should be broken. That's a negative feedback loop or negative feedback mechanism. I must have had all those blank, didn't I? That wasn't on purpose. Cool. Okay. So predicting climate change. Use a computer. And again, the movie The Day After Tomorrow. They were all in a rush to ask Jack, the climatologist, for his computer model, or to go ahead and see if he could predict the changes that were occurring quickly. I don't know. Anyway. But remember we said, and on your test you told me that short-term forecasts are more likely to be accurate than long-term forecasts. So they have that going against them. But I kind of laugh because if you are in this business, you could be totally wrong, predict what the climate change is going to be in 100 years. And in 100 years, frankly, you don't care because you're dead. So you would be less subject to given a hard time, depending upon what kind of your time range was. So there is that problem. So down here, this is kind of neat. The split there, the blue is actually natural variations in global temperatures that have occurred, and the pink is the actual, which is a combined of natural and man-made. So it's complicated, like I said, to make those models. I don't know. Better them than me. So here's a figure from your textbook that says, as temperatures of the Earth increase, what sort of things are we in danger of? So this is just simply the temperature increase, less cold days, precipitation changes, patterns, drought, probably hurricane will increase. One of the things with increasing temperatures is, let's see if they say it. No. Okay. Anyway, fire ants. Okay, so with warming temperatures, one of the things we have to worry about is rising sea levels. And it's been a while since I heard this on a podcast, but there are islands that are very concerned about the ocean's rising level all around them. And I think they're like wanting to sue industrial nations for rising sea levels related to global warming. I don't know, it's a thought. So sea levels rise because the glaciers melt, and kind of from left to right you see the same field of view. Over here it's all ice. Over here it's all icy. And over here it's a lake. So you're like, oh dear, that can't be good. Kind of sad. But the other thing is that when you take water and if you increase the temperature of the oceans, honestly, it's just going to swell. It's going to occupy more volume. So that's the thermal expansion that we're kind of up against. So you may have heard that, it's North America. You may have heard that actually our east coast is more susceptible to rising sea level temperatures than our west coast. Our east coast has like that kind of the slopey sort of coast, and our west coast is abrupt. So, I don't know. Let's all go to California. But the other problem, and this is kind of what we talked about with hurricanes, is that as sea levels rise, the coasts of most continents are hot spots for people to go to. So this is kind of on the left. There's a bird's eye view. The NP stands for North Pole, kind of looking down at the Arctic ice sheet. And you probably see kind of that blue region right here, kind of this blue region. That's how big the ice sheet was, kind of averaged between 1979 and 2000. That's how big it was. Okay? So 12 years later, this is how big the ice sheet is. Now it says minimum because actually those are summertime areas. Okay? And then this right here is to try to kind of, this edition of your textbook didn't have this, but I thought this was interesting. This downward trend is in the area of the ice sheet. It's been a year ago maybe that folks that say that the Earth's temperatures are not rising got all excited about an ice sheet down here, or part of the ice sheet down here expanding. They're like, see, look, how would that ice sheet be expanding? And I don't know. It's frustrating. Temperatures are warming. Not just in here. So your textbook says that actually in climates, in cold climates, not only do we have ice sheets, but the land vegetation is in permafrost, where basically you go down, I can't remember how far it is, but it's ice all the time. So this figure over here on the right actually is from your textbook, and where you see kind of the green, that is area that's being converted to vegetation. Vegetation is increasing, i.e. permafrost is decreasing. So permafrost actually has a positive feedback with regard to global warming, and it looks like this. Okay, with global warming, oh yeah, you don't have these either, do you? With global warming, your permafrost will thaw, and as your permafrost thaws, then that makes your ground less reflective. So that means your ground will absorb more radiation, and as your ground absorbs more radiation, that will warm the Earth. So that's what we call a positive feedback mechanism. And ignore that caption down there that says shrinking tundra in Siberia. It's a different figure. Are we almost done? All right. Oh yeah, I added this slide. So this is about pH. And remember that the pH scale is a log base 10 scale. So when we're over here on the right talking about a pH 8.2 to pH 8, that's a big pH change. Significant. One of the things, remember we talked about carbon dioxide dissolving in the oceans, but when carbon dioxide dissolves in the oceans, actually it just makes the oceans, or makes the oceans acidic by making it, turning it to carbonic acid. So what this is showing you in the region near Hawaii, basically the pH is decreasing. Remember, lowering pH is becoming more acidic. So one of the things that they're finding, marine biologists are finding, is that these cute little crustaceans, when they go to make their shells, they have issues when the pH is like that. Because actually more acidic conditions will dissolve their little shells. But I think aside from that, pH is important to marine organisms have adapted to a particular pH. You shouldn't change it. If you've ever had like saltwater fish, you know that they want it just so. Okay. So to kind of summarize, I didn't know how to summarize, but I kind of read the last section of what your author talks about, and This idea of, remember, climates are long-term, so actually, I think it's possible that climate change can kind of sneak up on you. And then again, the bullet number 2, I said at the beginning of this chapter that any changes we make now, it's going to be a delay when we see the positive consequences. The third bullet up there talks about actually climate changes have been known to happen abruptly if there's some sort of kind of trigger or tipping point. So scientists have their fingers crossed that that's not going to happen because they can't plan for that in their models. And then the last one is just kind of some sort of vague statement about politicians. But one of my things is that when people making decisions related to science say, well, I'm not a scientist, well, then ask a scientist. So, I don't know. Okay.